Hello and welcome to today's ACM Learning webinar. This webcast is part of ACM's commitment to lifelong learning and serving the over 100,000 computing professionals and students who are ACM's members. My name is George neville-neil. I'm chair of the ACM Practitioner Board, and it's my pleasure to welcome you today. We do have a slide on some housekeeping items, but we're going to try to move quickly past that because today's presentation will take up the full hour. Before we get to the presentation, I wanted to mention the ACM Applicative Conference, which is coming up at the beginning of June. The 1st and 2nd should be held at New York University in New York City. There is an applicative link in the resource list on your screen if you want more information about that. Applicative brings together researchers and practitioners to share the latest technologies and trends in computing, and this is our second applicative conference. Today's presentation is a pragmatic introduction to multicore synchronization by Samy Al Bahra. Samy is the CTO of Backtrace, a New York-based company dedicated to improving debugging technologies for today's complex applications. Prior to Backtrace, Samy was a principal engineer at AppNexus, where he played a lead role in the architecture and development of many mission-critical components of their ecosystem. His work at AppNexus was instrumental in scaling the system to 18 billion impressions with orders of magnitude improvements in efficiency. Prior to AppNexus, Samy was behind major performance improvements to the core technology of message systems. And before that, he was at George Washington University's HPC lab, where he worked on the UPC programming language, heterogeneous computing, and multicore synchronization. Samy's the founder of the Concurrency Kit project, which several leading technology companies rely on for scalability and performance. I know Samy because he's on the practitioner board with me and also is one of the co-organizers of the Applicative Conference that I mentioned earlier. He's a member of the Applicative Program Committee for the Systems Software Developer track. So without further ado, I'm going to let Samy talk about pragmatic introduction to multicore synchronization.
Great. Hey, everybody. Just a warning, there is a fair amount of lag, so just drop a message in chat if there are any issues. So this talk is about the mechanical sympathy of parallel systems on modern multi-core systems. We'll be focusing on the fundamental architectural constraints of these systems and exploring some of the technologies that have been developed over the last 2 decades to allow programs to scale on multi-core systems. A lot of the content in this presentation is available in an article form on the ACMQ, and you will find a link to that later in the presentation. So let's start off by looking at some of the principles of multi-core systems. What we're focused on for this presentation are cache-coherent shared memory multiprocessor systems. So cache coherency is what provides the eventual consistency of this shared memory. And we're going to begin with a simple example over here. We have 2 cores running on different sockets. They have a 256-byte write-back cache with 64-byte cache lines that are direct mapped. And we have a program that will be interacting with this shared memory. So this is core 0, core 1, each with a memory controller and some kind of memory interconnect, and each with local memory. So what we're going to do here is thread 0 is going to increment this variable x, which initially contains value 443 by 10,010, and thread 1 will go ahead and print out that value. So when this is compiled down, it'll consist of a load from memory, and this is mapped to the cache line down here. So the full 64 bytes are read into the cache, and the cache coherency protocol is what's providing the consistency guarantee. So over here we load it in an exclusive state, and then we go ahead and update the value of x. At this point, the cache line transitions to a modified state. Thread 1 begins execution of the printf statement. It ends up loading x. Now, in this cache coherency protocol, this will transition core 0's cache line from modified to owned, and thread 1 will read it in a shared state. In this case, a direct cache-to-cache transfer occurs, and now you have this consistent view of memory. So there are several cache coherency protocols out there, each with various trade-offs. For a long time, Messy was ubiquitous. These days, you have Messy on AMD architectures and Messif on AMD architectures, each with a different set of trade-offs depending on your workload. But generally speaking, they try to optimize for cache-to-cache transfers and try to minimize inter-cache traffic. So this is very important because the cache line is the unit of coherency. And in that particular example, you could see a fair amount of message passing occurs. So if you're sharing actively mutated state, you will run into a scalability bottleneck. So for example, over here, we have an array with 2 elements, and thread 0 and thread 1 are incrementing logically disparate elements of this array. And what ends up here is you have false sharing because they map to the same cache line. Here's another example. So over here we have an object that contains a read-write lock. This can be a read-mostly workload. You have 2 threads acquiring this lock in succession and just doing read-mostly work. So this is an actively mutated state. Regardless, you're going to end up with a significant performance bottleneck here due to false sharing. So with one reading, you could see we have really nice performance, but as soon as another thread is introduced, performance drops off. So one way to mitigate this is to introduce padding so that the actual values being interacted with are on a separate cache line. So this helps mitigate some of the problems associated with false sharing. So for this particular example, you do end up with significantly improved performance. Obviously, there are still some overheads in order to provide that provide the coherency guarantees. So performance is not the same as having a one reader in this particular workload. Another thing to consider, and I've seen this in a lot of real-world applications, is folks just end up padding everything. Always, that's not good. Always consider the access patterns of your workload. For example, if you're always going to mutate something, some items in succession, it may make sense to just pay the cost of the coherency on a single cache line, for example. And depending on your levels of contention, padding may not be necessary at all. And there are all sorts of other resource bottlenecks. So right now we're primarily focusing on, the serialization costs with respect to cache coherency, but these days you do have technologies like hyperthreading where you will end up sharing pipeline resources across logical cores. And, the threads in this workload, you end up contending over pipeline resources. So there's all sorts of resource sharing that occurs under the covers. So a lot of the concurrency primitives you work with are implemented in terms of atomic operations, and these atomic operations are typically implemented with the help of the cache coherency mechanism via cache line locking. Back in the day, a lot of smaller scale systems relied on bus locking. So, for example, on the x86 architecture, older processors would literally lock the memory bus as a whole in order to implement these atomics, which clearly does not scale. Cache line locking, on the other hand, only serializes access to the target cache line. So here's some pseudocode for what a compare and swap operation would look like. You would essentially load a value from memory and mark that cache line. If the values compare, you go ahead and store the value of new, and then you could unmark that relevant cache line. So one thing to note here, I mentioned bus locking. There are still cases which will trigger bus locks. For example, if you execute an atomic operation which splits a cache line, you will end up with a bus lock. So that is something to be wary of as well. So atomic operations are typically what's used to implement concurrent synchronization primitives, as they provide atomicity guarantees very cheaply. The most popular primitives today are compare and swap. So if A and B are equal, then set A to C, or the value the object pointed to by A to C atomically, and load linked store conditional, or LLSC. So it updates A to B if A was not modified between the load linked and store conditional operation. And there are some trade-offs between these two primitives. Compare and swap is available on x86 and Spark architectures, as well as a bunch of others. LLSC is what you would see on ARM and the Power architectures. Another very important factor to consider in today's multi-core systems is they are NUMA architectures, meaning the cost to access different types of memory varies. You have, over here you have a diagram of the Nehalem processor, and you can see you have L1 level of cache. Over here you have an I cache and D cache, an L2 cache. You have some logic in the uncore in order to provide consistency guarantees, among other things. So this actually implements a coherency mechanism for you with the help of the underlying buses, as well as local RAM. So the cost to L1 to registers is significantly lower than L1, significantly lower than L2, significantly lower than the uncore, and then significantly lower than DRAM. The NUMA factor is the ratio that represents the cost of a remote memory access. So over here we have the results of a very simple benchmark, which was just doing a point-to-point wake up from 2 threads. And over here we can see the cost of local wake up is significantly cheaper compared to the cost of a remote wake up on a thread on another socket. This is very important to take into account. NUMA factors can be very difficult to mitigate. Many years ago, I was doing some work at the Arctic Region Supercomputing Center, and they had just ordered a new 8-socket system. And there were issues with performance there, primarily due to the coherency overheads. There were up to 3-hop distance between nodes in certain cases. Over here, we had a simple benchmark, which simply executed get time of day on different cores on the systems. So on Linux, get time of day is implemented with a shared page, which was typically pinned on the first core of the system. And you can see you end up with some significant differences in latency of the system call, depending on the core that you are executing in. There are also implications on memory allocation. So typically today, most systems will have a first touch policy. So whenever you touch a page of memory, it ends up being mapped from the processor, which the thread is executing on. It's also possible to use an interleave policy on many systems, such that pages are allocated in a round-robin fashion across nodes. And there are trade-offs with each. So, for example, if you high amount of data sharing across all your threads, you may want to optimize for throughput, at which point you want to interleave if you don't want a particular hotspot. But if your data is going to be local to a socket, you definitely want to make sure to take advantage of your first touch policy. A lot of systems, for example, they will have some kind of initialization phase on startup. Some thread will be running on some core and end up generating a whole bunch of configuration state. That configuration state may be pinned on a particular core, and you will end up with hotspots. So these are all important things to consider. Another important factor is if you're using a synchronization object, like a read-write lock, or some type of a mutex, for example, and it is NUMA oblivious, you can end up with very significant performance artifacts. That's not just starvation, but you can even have live lock under very high levels of load. So in this particular example, we have a bunch of threads executing on an Intel processor. Each thread is pinned to a separate core with a tight loop doing lock acquisition. This is a very simple exchange-based lock. So it's, bare bones. And you can see there is a huge trade-off as far as fairness is concerned. Some of these cores are just significantly underserved. So one approach to mitigating this is to use a fair lock. So ticket locks have been around for a long time now. They got a bit more love and attention a few years ago due to some work that Nick Piggin did for SUSE, where they introduced this for the Linux kernel. So the way the ticket lock works is every thread, every potential, every acquisition request is provided a unique ticket number. So we'll do a fetch and add on this next counter. And then you'll spin until position is incremented to next. So assuming that your underlying hardware resources are not overcommitted and you don't have starvation issues there, you do get not only just starvation freedom guarantees, but you also get FIFO fairness guarantees as well. So this is the same benchmark as previously. So FAST is a fetch and swap, exchange-based lock, and the blue bar is the ticket lock. So over here, you can see that the ticket lock does provide starvation freedom guarantees. You definitely have fairness. Another important thing to note, however, is there's definitely a trade-off in overall system-wide throughput. So fair locks are not a silver bullet, and they can negatively impact throughput. Another important factor to consider is even if you did have a scalable fair lock, that cost, at least in the user space, if you do have sources of jitter, can come at increased cost. So there will also be a trade-off in throughput in that situation as well. So for example, over here, we're using a scalable MCS lock, which is a queue-based distributed lock. And we'll get into that in the following slides compared to the ticket lock. And you can see some significantly improved performance here. In this particular scenario, the MCS lock is distributed. And what that means is threads spin on local memory and do point-to-point wake-up. So the red circle here represents the MCS lock, and these set of threads are going to go ahead and acquire the lock. So what thread 1 does is atomically sets the MCS lock to its own lock record, essentially. And at this point, it would have acquired the lock. And when thread 2 comes in, it'll go ahead and do something similar, but it'll detect that another thread has the lock acquired, and it'll go ahead and link itself to that thread's record, and spin locally. So this is very important. Every thread is essentially spinning on its own set of cache lines. Once thread 1 has completed its work, it'll do a point-to-point wake-up to thread 2 and essentially update thread 2's record to indicate that it now has acquired the lock, and so on and so forth. So there are a whole bunch of other schemes in there. So MCS gets a lot of love. There are, the CLH lock is an alternative to MCS, which actually has a significantly faster path. It only requires a single exchange on the fast path. MCS is significantly heavier weight on the fast path. You could also implement distributed locks with asymmetric synchronization primitives such as a read-write lock. So a traditional read-write lock, and we saw this in one of our earlier examples, readers and writers may be spinning on the same cache line, or at the very least, readers will be spinning on the same cache line. And, earlier we had mentioned there is this cache currency mechanism, and cache line is a unit of contention. So even for a read-mostly workload, you'll end up with significant scalability bottlenecks. So another approach here is to actually distribute the read side words across the cache lines that the threads are running on, and have those threads spin on those cache lines instead. So Linux had a variant of this called brlocks for a very long time, and FreeBSD has a more sophisticated variant called read mostly locks. And essentially, read side flags are distributed in some fashion across threads. So here's a benchmark where we compare the big reader lock to a centralized read-write lock. So this is a read-mostly workload. So you have a bunch of threads spinning in a tight loop, and they're just acquiring the read side critical section. And you can see that the centralized, traditional read-write lock simply does not scale, while the big reader lock has no issues whatsoever. Essentially, the cost is serialization of an atomic operation on the fast path and some form of serialization on the pipeline. So one issue with locks is they're not composable, and they're susceptible to a myriad of issues. Not just performance issues, but correctness issues as well. And really using them wisely is more of an art rather than a science. There's a very delicate balance between how you want to organize locking hierarchies, how large you want your critical sections to be, and the sorts of progress guarantees you want to provide. So in the prior graph, I'll just load that up again very quickly. Everything is nice and predictable. But let's go ahead and just introduce a single writer to this workload. So this is still very much a read-mostly workload. And you can see performance is sort of all over the place. So one way to mitigate this is to rely on lockless synchronization. So rather than reasoning in terms of lock dependencies and critical sections and building data structures on that, let's instead build data structures on the atomic operations that the underlying platform provides us. There are a lot of difficulties with this approach, or dealing with a much larger state space. So in order to explore lock synchronization, let's first go over some fundamentals of memory models. So cache coherency helps implement the consistency model. The memory model actually defines the correct behavior of shared memory axes. So let's walk through a simple example on a commodity x86 processor, which is using total store ordering. So in this case, you have two global variables, x set to 0 and y set to 0. Core 0 has a local flag R0, core 1 has a local flag R1. Core 0 will set x equal to 1 and then store y into R0. Core 1 will store 1 into y and store x into R1. Now, assuming that this is executed in a serialized fashion, we should never observe this state, right, where R0 is 0 and R1 is 0. So, for example, assuming these are essentially executed in a lockstep fashion. So after x equals 1 executes completion, y equals 1 executes completion. These are the values you would observe for R0 and R1. And this is totally fine. And even if you reorder this, so let's say that the x equals 1 core 0's operations execute before core 1 is completed, you would see 0, 1. So these orderings are all permitted. It's all serialized stuff. But unfortunately, with today's processors, you can end up with all sorts of interesting reordering. So the processor will reorder its operations in order to optimize for various resources. So it is, in fact, possible to observe R0 and R1 equals to 0, 0, which would only be possible if the store to x and the store to y are reordered prior to the reading of y and reading of x. So the processor isn't actually trolling you here. So as I had mentioned, the processor will do all sorts of things to optimize for performance. Specifically, a lot of those techniques are in order to improve levels of instruction level parallelism. So this is a simplified diagram of a modern processor, and you can see there are a bunch of things prior to the rest of the memory hierarchy. More specifically, you have some kind of memory order buffer, which will contain some kind of a store buffer. So over here, we set x equals 1 in core 0. We set y equals 1 in core 1. And we go ahead and satisfy the reads of R0 and the read of R1 from main memory. The stores to x and y have not yet been flushed from these processors' memory order buffers to the memory hierarchy. So this is a store-to-load reordering, and all architectures have this, and it's something to be wary of. Different architectures have different ordering guarantees. So TSO architecture, so that's x86, Spark has a TSO mode. I believe ARM v8 has a TSO mode as well. Don't reorder anything except for store to loads, and they provide ordering guarantees on atomic. So if an atomic operation executes, all prior operations are serialized with respect to that atomic. Relaxed memory ordering architectures are also ubiquitous. So ARM processors, for example, which is probably what's running on most of your phones, can reorder pretty much any memory operation with a few exceptions. So a lot of you are familiar with traditional synchronization primitives, and you might ask yourself, like, okay, how come I never had to worry about this before? Traditional synchronization primitives typically provide some serialization guarantees, and they use special instructions to implement those. So, for example, over here we have a critical section where x is incremented by 1 under a mutex. The reason this operation is not reordered outside of the critical section is the locking mechanism itself will use a special instruction to provide that guarantee. So in this case, mutex lock. Over here we're using a bunch of concurrency primitives, so this is a atomic swap. It'll, in a tight loop, it'll try to set value to true and grab the previous value, and it'll continue spinning until it encounters value of false, meaning that it has acquired the lock. Most importantly, though, you can see this fence memory operation, which guarantees that no memory operations prior to the fence are ordered past the fence, and same thing for for operations after the fence. Now, these operations are expensive. That is very important to take into account. I've seen many cases where folks are like, oh, let's just use an atomic increment operation. It's going to scale, or it's going to perform well. Now, assuming it's distributed, yes, you will achieve scalability, but there is still a cost on the fast path. So on x86 architectures and other TSO architectures, these atomics do provide serialization guarantees, which does disable a lot of the pipeline optimizations that your processor has. So what we're going to do now is actually explore a bunch of algorithms you can implement on top of these atomic operations. So lockless synchronization is exactly that. It's not a formally defined term. It's synchronization without locks. You could have things that look like locks in there. What we're going to focus on is non-blocking synchronization. Non-blocking synchronization provides very specific progress guarantees and very strong properties in terms of resilience. However, there is a cost to the fast path. So lock freedom provides system-wide progress guarantees. We'll revisit that shortly, but essentially, for example, if you have a bunch of threads executing some operation on a data structure, it's guaranteed that at any point in time, at least one thread will be making forward progress. Wait freedom provides per operation progress guarantees. So taking that same example, if you have a bunch of threads executing some operation on a data structure, all those operations are guaranteed to complete in a finite number of steps. So one of the simplest examples here is a stack. So here's a traditional stack in C. You have a node which contains a value and a pointer to the next node. In push, push takes a node, a value, in the top of the stack, and it will set the value and then set the next pointer of the supplied node to the top of the stack, and then set the top of the stack to the node. Pop will read the top of the stack, and then set the top of the stack to the next node relative to the top of the stack at the time stack pop was called. So what we're going to do is turn this into a lock-free push operation. So we're going to rely on the compare and swap operation here. So we're going to store the value into the supplied node, and then we're going to take a snapshot of the top of the stack. We're using a load pointer here. This is just an atomic load. And then we're going to set the top of the stack to our snapshot, assuming the top of the stack is still equal to our snapshot. And this is using the compare and swap operation. So you can read this as if top of stack is equal to entry next, then set the top of stack to entry. So this is a lock-free progress guarantee with respect to stack push. So, various threads, for any number of threads that are executing, it's guaranteed that at least that one thread will be making forward progress. And stack pop is implemented in a similar fashion. So we take a snapshot of the top of the stack, and we look at the next node relative to the node that was on the top of the stack. And if the top of the stack hasn't changed, then go ahead and set it to the next node. And again, we have lock-free progress guarantees here. So assuming you don't do things like use dynamic allocations, or if you're using a garbage collected language, then you have a lock-free stack implementation here. There are still some issues around memory management, and we'll actually get into that shortly. So an important thing to know is non-blocking synchronization is not a silver bullet. There's a lot of hype around these data structures. The assumption is that, hey, if we're using a lock-free data structure, you automatically get scalability, etc. That's definitely not the case. Generally speaking, if you have a generalized lock-free data structure, it will have a higher cost on the fast path. And there are no guarantees as far as scalability is concerned. If you're still sharing actively mutated state, you will have a scalability bottleneck. So over here, we compare the cost of a stack that's protected with a spin lock, its push operation, and a lock-free push operation on an x86 processor and a power processor. So x86 is using comp exchange, power is using load length store conditional. And these are the pop operations. So for example, over here, you can see the spin lock protected stack, at least in the uncontended case, actually has significantly better performance than the lock-free implementation. And that's because the spin lock-based stack relies on a very cheap atomic operation on the fast path, and it's one atomic operation. On the other hand, the lock-free stack requires a much more complex comp exchange instruction. So you end up having to spill a lot of things from registers to memory, and there are just more of these serializing operations on the fast path. On the IBM Power, on the other hand, you'll see that the lock-free stack is significantly faster than the spin lock-based stack, and that's because we can actually get away with cheaper memory fencing operations on the fast path and fewer atomic operations as well. So really, they're not a silver bullet. You really have to consider your underlying memory model and the underlying processor. However, where they do shine, generally speaking, across the board, is under contention. So under high levels of contention in a lock-based stack, any source of jitter will essentially block system-wide progress, right? So if a thread is pushing items to a stack and it's interrupted by a timer, for example, no other thread can make forward progress on that stack. The lock-free stack, on the other hand, has much stronger progress guarantees. So this graph has the latency distribution of push operations on a stack under high load. and again, you can see the lock-free stack has significantly better latency distribution. Another thing worth noting here is the lock-free stack does not actually provide starvation freedom guarantees. So starvation freedom guarantees are ultimately only two things. For a lock-free stack, you have for lock-free algorithms, you don't have any of those starvation freedom guarantees. And even if you have something that's weight-free, so let's say you're simply doing an atomic increment, those progress guarantees are only going to be as good as the progress guarantees of your underlying hardware. Now, let's say we do want performance. There are actually cases where you can extract a lot of performance from your in a concurrent algorithm, but you will require some form of specialization. So either it's not correct under all circumstances, or you constrain runtime requirements. So one common thing, for example, is to assume only a single writer. You can do all sorts of interesting things. So for this, we're going to we're going to use this lean startup database, employee database example. So over here, we have a lean startup with 8 employees, and you have an employee type where every employee has a name and a number, and then a directory object, which consists of an array of pointer to employees, up to 8 employees, and a read-write lock. We have an employee add operation where given an employee's name and a phone number, they'll be added to the directory. Given an employee's name, they'll be deleted from the directory. The constraint here is your lean startup will never hire employees with the same name. And number get, so return an employee's number given their name. So let's look at what this looks like using control read-write synchronization objects. So over here we're using a read-write lock. This is what number get may look like. So over here we acquire the read-write lock. We'll iterate through every pointer in this array. And if the pointed to object's name matches the name that we requested, then we will go ahead and copy the number, unlock the lock, and return the number. So fairly simple here. However, an important thing to note is the correctness guarantees here do come at the cost of forward progress. So when the read lock is held, no writes can occur. And this is what the add object would look like. You know, there are certain things I do here which you should not be doing. For example, you should not be allocating memory underneath your critical sections on the fast file. But this is just for the sake of this example. So we acquire the write lock, and we will allocate an employee object, and we will set the name, set the number, and then set the array position to that, and then remove the write lock. Again, this operation will only execute in the absence of readers. The other interesting thing here is, and delete is also very similar. Just for the sake of time, I won't go into that too much. So, an important thing to note with the delete operation, so we'll acquire the write lock, loop through every member in this array, and then essentially guarantee that the employee object that we found is no longer reachable. We set it to null, and we make a copy to a copy of the reference to that employee object and delete the write lock. At this point, it's guaranteed that any readers that come in will not be able to interact with this the object which we just deleted. And due to this guarantee, we can actually just free that region of memory and allow for reclamation to occur. So in this case, the reachability of the employee object and its liveness are coupled. So we protect, again, what is called a read-reclaim race. And this is just another visualization of it, somewhat terrible visualization of it. So you have thread 0, which is a writer, thread 1, which is executing a read side operation, as well as thread 2. And when thread 0 begins this delete operation, it has to block, because it's executing write lock, until all readers have completed their operation. They're out of their read side critical sections, at which point readers cannot acquire a read side critical section until the write lock is released. And at this point, it's free to delete that object. So this is a very typical pattern in concurrent data structures. Another pattern for these data structures is reference counting. So there are cases where you may actually have to decouple reachness and liveness, reachability and liveness of the object. For example, you could have very long very long-lived references to these objects. So in this case, we have a read-write lock. Excuse the API change. So this is pretty much the same semantics, except it's a big reader lock. And we will loop through, find a match, and then atomically increment a reference to the employee object, which matches the incoming query before releasing the lock and removing and returning that employee object. Now, when you actually go ahead to delete the object, rather than immediately freeing the object, you'll actually rely on this reference count. So over here, rather than calling free, now we'll call employee delref whenever we are done using a particular employee object on the read side. So what that will do is atomically decrement this reference count, and if the reference count is 0, then it is safe to physically destroy that object because it's guaranteed to no longer be reachable. And this is what it would look like on the right side. So on the right side, on the delete path, after we find the relevant employee object, we will guarantee that's no longer reachable, and then we will atomically remove that reference count. And the last thread to remove its reference will be responsible for physically destroying that object. And essentially now what you have are two phases. You have a logical deletion and then an actual physical deletion. So thread 0 here does a bunch of logical deletes. Thread 1 acquires a reference to an object, same as thread 2. And thread 2 is the last thread to remove its reference, so a particular employee object, and now it is responsible for deleting that reference. Now, earlier I had shown you a bunch of graphs showing the issues with forward progress guarantees with read-write locks. So what we're going to do now is actually start stripping these locks. So we're actually going to remove right side locking. We're going to remove read side locking and assume there will only be a single write lock. And we're going to use atomic operations for this. So over here, we acquire the write lock for add. And what we do is we allocate the employee object, set the various fields. We use a store fence to guarantee that these operations will be globally visible before we update the array. And number get now actually has no locks whatsoever. So this scales perfectly, and there's essentially no cost on the fast path, at least for most architectures today. So what we'll do is loop through, we'll do an atomic load for every element in the array. And we'll use a fence here. This fence is not really, it's not needed for any architecture that matters this day. Alpha would require this type of fence, but we don't need it because we have a data dependency. So assuming that we match, we could go ahead and just return the phone number. So over here, readers do not interfere with writers whatsoever, and they don't interfere with each other. And again, on x86, this gets compiled down to plain old memory loads and stores. So it's pretty much the ideal algorithm for this read-mostly workload. However, there are some problems. We'll get into that shortly. So let's just look at the performance properties here. Over here on delete, this is where we actually encounter the problem. Sorry about that. I actually skipped the slide locally. So on delete, we'll loop through this array. We'll acquire the write lock, loop through the array. We'll use atomic operations to guarantee that this member of the array is no longer reachable. But now we run into this problem in that when is it free for the writer to actually physically destroy the employee object? The read side operations are not synchronizing with the write side operations whatsoever. And for this, we need to apply more advanced techniques. So before diving into those techniques, let's just revisit the performance properties. So this, lean startup example will be executing under, we'll have a uniform read mostly workload. So we're primarily reading. And then a writer will come in every couple thousand operations, 10,000 plus operations, and do a pessimistic add operation. So it'll add something to the end of the array. And readers will be in a tightly trying to get the number of the first employee. So it's a very simple workload. This is running on a 12-core system across 2 sockets. And various measures were taken to minimize jitter. So things are running in the highest priority, and I'm not playing any video games on this particular box. So this is a read latency as we increase the number of processors. And there are no updates occurring. So this is pure reads. And as expected, we see that the read-write lock does not perform well. And the big read lock and reference counting also has the same issues. So an interesting thing here, even though this is a read mostly workload, it's turned into a write heavy workload because of the reference counting that occurs. So since those reference counters are sharing the same cache line, if you have multiple readers interacting with the same object, they end up having to serialize behind this actively mutating state. So the concurrently readable algorithm, which is the algorithm that doesn't have any locks whatsoever, performs the best. So there's essentially no cost on the fast path. And the big reader lock is slightly slower, but it actually scales linearly as well. There are no updates, scales perfectly here as well. There are no updates on the fast path. So this is to be expected. And this is reflected in this graph as well. So you can see there are some overheads, even with a distributed lock, because you do have some synchronization that has to go on. So now if we introduce a single writer, performance is all over the place for any of these blocking synchronization primitives, while the concurrently readable version has terrific performance for readers, right? Readers are not blocked whatsoever on writers. And even the writer has amazing performance here because it is not blocked on readers, generally speaking. So the only problem now is, we have this amazing concurrently readable algorithm. It's a single writer algorithm for this directory object, but we have no way to actually reclaim the memory. So if you delete an object, we can't actually an employee object, we can't physically destroy it yet. And the reason for that, as mentioned earlier, is we have this issue of a read reclaim race. So the object would be destroyed when there are active references or axes to it. So over here you have thread 0 attempting to free an employee object, while thread 1 is axing fields within that object, as well as thread 2. So there are a whole bunch of techniques in order to protect against these read reclaim races. Some of the more popular ones are hazard pointers, quiescent state-based reclamation, and epoch-based reclamation. Quiescent state-based reclamation is heavily used in the Linux kernel, as well as various variants of it under the flag of read copy update. And if you're interested in that, there are also a whole bunch of articles on the ACMQ. So Paul McKenney, who did a majority of the work for RCU, has a bunch of papers on this. So QSVR and EBR provide protection against read reclaim races without affecting read side progress whatsoever. And some variants of QSVR, for example, don't require any additional overhead on the read side. However, the trade-off is writer progress would be affected. So what we're going to do is just implement a toy implementation of this hopefully in 10 minutes, or I'll be over time. One thing I should know before we dive into this is relevant for any language which lacks a GC. So if you're using an unmanaged language, you'll need techniques similar to this in order to use dynamic data structures. Or you could simply recycle regions of memory, for example, with a lock-free stack or similar. But there are trade-offs with that. So these are what the operations look like for the scheme we're about to implement. You have a read side, a read lock, and a read lock operation. This could also be called read begin, read end. I prefer the begin and end naming. It's clear that there is no exclusion occurring as far as forward progress guarantees of readers and writers necessarily. And then you have an explicit reclamation operation, synchronize. And essentially what synchronize does, so over here you have thread 0, which is a writer, thread 1 and thread 2, which are readers. The green items are essentially idle states. So at these points in time, the threads are not doing any work. And the blue are the blue blocks under the read side are active read side operations. So for example, number get would be an example read side operation. And what the synchronize operation does is block the calling thread until all currently executing read side threads are in idle state or have progressed past the next idle state. So over here, thread 0 calls synchronize at this point in time, and it will block until all threads are done with their read side critical sections, which is at this point in time, and this is known as a grace period. So at this point in time, the logical delete, which occurred prior to the synchronize operation, is guaranteed to be visible to all processors. And all subsequent read operations will not be able to acquire a reference to the logically deleted item. So we can be confident in the fact that we can physically destroy said object. So let's look at a toy example. So over here you have, just to clarify that point a little bit, over here the right side delete operation will store null into the slot we're trying to delete. It'll call synchronize, wait for all readers to finish the read side critical section. All readers are idle, and then it can physically destroy the object. The readers are in a tight loop, calling employee get, doing stuff with the employee object, and then calling quiesce periodically to indicate that they are making forward progress and they're in a quiescent state. This is a point in time where no active references exist to objects which may be subject to a read reclaim race. So down here we have an execution history of what that would look like. So we store null into the slot of the employee object we want to delete, and we call synchronize. And synchronize will wait until all readers have at least called quiesce one more time before returning. And now the guarantee is any subsequent, at this point in time, any employee get operations are guaranteed to no longer be able to reach the deleted employee object because we set that slot to null. And at this point in time, we're actually free to physically destroy that object. So what's one way to implement this? So over here, we are using a global counter. And what synchronize will do is it will execute strong fence, a full fence, in order to guarantee that all prior operations are globally visible. This is executed by the writer and ordered. And it will increment this logical clock. And then it will wait for all readers to observe this logical clock. Now, readers will be calling quiesce at some fixed point in time. And what quiesce will be doing, simply, is reading this value of the global counter. So what this means is whenever we call quiesce, we're going to increment value to some new value never seen before. It's a monotonic counter. And if all threads have observed this new value, then we can be rest assured that any of the operations prior to synchronize, such as logical deletes, are globally visible. So this is an example of safe memory reclamation. This is a very simple toy implementation of RCU. So this pretty much covers the essentials for, we covered a lot of the basics of multi-core architectures and processor architecture as they are related to multi-core programming. We covered the issues with scalability, avoid sharing actively mutated state as much as possible, and hopefully have more of an understanding of the intricacies in lockless programming and some of the additional things you have to take on, such as more complicated memory management schemes for dynamic structures. So you can follow me on Twitter. That's my Twitter. Concurrencykit.org is a BSD licensed open source library which contains a lot of concurrency primitives and reference implementations for these algorithms. It's C99 and BSD licensed. And if you go to backtrace.io, we have a blog there with a bunch of articles related to concurrency. A lot of the content here can be found on the ACMQ as well. So there was an article that I wrote which covers all this material. And frankly, I did a better job in the article than I did in this presentation. And there are a whole bunch of other articles on there by Paul McKenney, Magid Michael, and Matthew Desnoyers. There is also an upcoming article by Andrew Morrison on how to scale contended data structures. So I think at this point we're ready to go to questions.
Okay, thanks, Samy. We have a number of questions, so I'm going to probably not get to all of them, but let's see how many we can get through in the next few minutes. One of the ones that someone had labeled as for after the talk, so I'll do this because it's after the talk. The question is there a great book you can recommend that covers synchronous and asynchronous fundamentals and when to utilize certain types of locks?
Sure. So unfortunately, there aren't any books that dig into the details of when to use specific types of locks with different kinds of biasing. However, the MCS paper, so Scalable Synchronization for Shared Memory Multiprocessors, is terrific. It's 40-plus pages, and they do an amazing job covering the various scenarios and performance properties of various locking implementations. The authors did win a Turing Award for that work, so I would highly recommend it. In addition to that, there's terrific work with phase-fair read-write locks. The authors do an amazing job there, really distilling the effects of biasing for asymmetric synchronization primitives. So those two papers are very approachable. Whether you're an academic or practitioner, they're both very easy to read. And then last but not least, if you want a book that'll just give you a really terrific overview of both the theory and practice of multiprocessor programming, The Art of Multiprocessor Programming is definitely a classic in this area.
Okay. Next question is, what's the best way to debug programs around these kinds of locking primitives?
It really depends on the problem. So there's a whole myriad of techniques there. So there are a lot of model checkers out there which do support some of the instruction sets that matter. Unfortunately, that isn't tenable for a complex system. So if there's a great article by Paul McKenney on Linux Weekly News where he introduced CMEN and basic use patterns there. Dmitry Vyukov also have Relicy, which will do it'll essentially explore the state space of any concurrent algorithm they'll feed it, and that's grounded in C++. Another approach here, of course, is to rely on deterministic multi-threading and reversible debugging. So depending on the level of granularity that you need, you'll have limited success there, or if you have timing constraints, you'll have limited success there. But I would definitely check out R2 as well as other tracing technologies. And typically speaking, I rely on traces if I'm ever debugging an issue of that kind. And then last but not least, if you are in the unfortunate position of having to implement some of these more involved primitives, applies some sort of formal reasoning to it. Even case-by-case analysis is feasible if you do constrain some of the runtime constraints, constrain the correctness constraints. For example, if you have a single writer. So if you're interested in learning more about this, Matthew Desnoyers has an article on the ACMQ where he reviews a bunch of these techniques.
Okay, and I think we're going to probably come down to our last question since we're coming up to the top of the hour. One of the questions has to do with the Boost libraries, Mutex library, in relation to this kind of synchronization. What do you think of their sort of synchronization primitives? Have you looked at that at all?
No, I'm not familiar with Boost implementations. Generally speaking, all these libraries tend to have very heavyweight implementations that are targeting general purpose computing. So the types of workloads I deal with are typically single application servers, and we optimize performance for that given application. We're trying to optimize resources for that.
Okay, and that brings us exactly to the top of the hour. So thank you, everyone, for listening. We've run out of time. I'd like to thank Samy Al Bahra for his amazing presentation, which is incredibly dense and has quite a number of pointers that people should go look at later. And thanks to everyone for being part of the webinar.
Yep, and if anybody has questions, feel free to tweet at me.